Okay, so today is Tuesday, 11:15, and so keeping with our theme of Tuesday, Wednesday, and Thursday being past, present, and future, we're going to review decimals and numbers that have decimal places. So the reason for this is I see from time to time that it doesn't appear to me that certain students or even possibly a majority of students sometimes have a real firm grasp on exactly what decimals are, what numbers that have decimal places mean, and generally just what the concept is. So to illustrate, I'm going to start out with a question. So you can see these two numbers here, 2.8 and 2.4567889. Okay, now I need you to ask yourself which one of these two numbers is larger. Okay, so just think about that for a second, pause it if you need to. But if you chose this number, then this lesson is for you, because this number is indeed not larger. Okay, this is the larger number. Okay, and we're going to go over that, and hopefully by the end of this lesson you will realize why. Okay, so another question, and hopefully this can spur some thought here. So you may know that this number is in what we call the tenths place. Okay, now question is, if we were to add all these numbers, okay, let's just say we were to add all of those numbers, the 6 all the way out here to the 9, would they ever equal this number? Furthermore, what if we were to just keep adding 9s? Maybe another question is, how many 9s would we have to add before the total of all the numbers that we've written, if we added them together, would they equal this 4, or maybe possibly be larger than the 4? Okay, so pause and think about that for a minute if you need to. But the answer is there are no amount of numbers, no amount of these numbers. It doesn't matter. We could keep on writing 9s for the rest of our lives, and it will not only never equal 4 in the tenths place, the sum of those numbers will never even equal 1 in the tenths place. So we're working with 4, but all these numbers out through here, if we added them all up, they would never even equal a 1 in here. They could come really close, but they would never equal 1. So that's pretty intense fact if you're just hearing that for the first time. Hopefully by the end of this lesson you will understand why that is the case. But both of these things, if you were thinking about this seriously and you were thinking, I don't know, how many numbers should I write before I could add them all up and they would equal 4? And I'm not talking about the individual digits, I'm talking about what these numbers actually represent. So this is a 7 in the thousandths place, not just the number 7, okay? This is an 8 in the 10,000ths place, okay? So that's an 8 in the 10,000ths place. I don't know if you can do that, but it's an 8 in the 10,000ths place. And so on, the 100,000ths, the millionth, just on and on and on. Okay? So if you were to sum up all these, you could never even equal 1 of these in the tenths place. Okay? And it goes on similar to that. You could pick any number. You could pick that number or whatever place that is, the millionth place, I don't know. But if you summed up all these numbers, they could never even equal 1 of that number 9 right there. Okay? So here is why. Okay? Well, first of all, we're going to start out with, what exactly is a decimal? So a decimal is just a way to represent a number that is smaller than 1 or any number that falls between two whole numbers or integers. Now you kind of use the term whole number and integers interchangeably here. They're not interchangeable, but we can stick with whole numbers just to illustrate the point. But integers would actually be the proper thing because all this works with negative numbers as well as positive numbers. So the first thing we need to understand is the number before the decimal, as in this number. That's just the whole number. We know about whole numbers. We don't need to go into that. In this case, there's 1. It could be 2, could be 3, could be any number. That's just a whole number, okay? We know what that is. These are the ones we're concerned with, okay? So you know how decimal works.
Ms. Traeger, if you're in the building, I'm a visitor at the front office. Ms. Traeger, you have a visitor at the office.
Okay, maybe we're going to have a bunch of announcements today. So anyway, these are the numbers after the decimal point that we're interested in, okay? So there is the tenths place and the hundredths. Let's do that a little neater. The hundredth. That's DTHS, hundredths place. Then we have the thousandths place. So the decimal, when you're talking about the tenths place, what you're talking about, and I'm just going to draw these little bars here. I may have to do some erasing, so let's erase that. Go back, you need to label the spaces. But let's just say that these bars represent, we're going to imagine that they're all the same size. Okay? They're all the same size, and they all mean something. We're going to say that they all mean the number that they're next to. Okay? Now, what do I mean by they mean the number next to them? So if you have one bar, and you color in, let's say, you don't divide this bar up at all. You get to have the whole bar. So we'll call it a candy bar or whatever. So you get to have the whole bar, so that bar represents this one. There is one of those bars. Now, when we go one place past the decimal, so we go to the tenths place, we're essentially taking 1, the whole number 1, and we're dividing it evenly into 10 parts. So how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's actually 11 parts, so we're just going to act like that top one is thick. So let's just pretend that this bar was divided into 10 even parts. Well, one part would just be one of these little parts. So it's just a small, it's a lot, obviously, a lot smaller than this over here, right? Because it's just 1/10, okay? Now, let's also imagine, we're going to go to this bar. We're going to the hundredths place now. Let's try to imagine that we could, if we wanted to, divide this bar into 100 equally sized parts. So imagine breaking a candy bar up into 100 equally sized parts, which I can't actually do, but we can imagine it, okay? So what would one of those parts be? It would be a little tiny, tiny sliver, okay? Tiny. Much tinier than this, much tinier than the tenth, and certainly much tinier than your entire bar. So as you can see, each place we go, the numbers get smaller and smaller. And not just by a little bit, by a factor of 10 actually, or divide by 10 or whatever. So you can see that they're getting a lot smaller each time we move. Each time we go from the tenths to the hundredths, and now we're on to the thousandths, the numbers in those places are getting a lot smaller, okay? So let's also pretend now that we could divide this bar up into 1,000 equal pieces. Imagine a candy bar divided into 1,000 pieces. What would one of those pieces be? just a tiny little speck, just nothing. You could probably barely even see it. So obviously that would be even smaller than this little strip when we divided our candy bar into 100 pieces, and definitely a lot smaller than a tenth of a candy bar, and you just can't even compare it to a whole candy bar. They're just in two different worlds, basically. So that is how a number with decimal places is constructed. But more specifically, if we're trying to make sense of a number with decimal places, okay, we're going to look at a specific number, and it's actually the first, if you want to rewind, but there's no need to, it's the first 4 digits of the big long number that I asked you about at the beginning, okay? So the following number, you know, it falls between 2 and 3. So the job of decimals are to represent numbers that are between integers, okay, or whole numbers. So if you have negative 2, and negative 1, and 1, and 2, and we'll say 3. Well, our number here, our 2.467, well, it's more than 2, but it's less than 3, so it falls somewhere in here. And that is the job of the decimal places, is to tell us exactly where it falls. And decimals have a larger function, which we'll get to at the end of it. But for now, that's what they're there to do. So the whole number is just a whole number. We know what that is. It says there's at least 2 of whatever we're doing. Well, since we have some numbers in the decimal places, the first 3, the tenths, hundredths, and thousandths place, we know that this number is more than 2, but not quite 3, or not even close to 3. It's about halfway in between, but we know that it's between 2 and 3, and that's what decimals are for. They're for numbers that are between whole numbers or integers. Now, how do they work? So this slide may be a little redundant. Yes, it is. Skip it. Okay, so how much more than 2 is 2.467? That's what we want to know. Because it's certainly more than 2. But how much? We need to get a feel for where it lies between 2 and 3. Okay, so the first thing we need to look at is this 4 right here. So that 4 is in the tenths place. The tenths place. Now what that 4 literally means is we can take a whole number, just like we had our bars before. Okay? So this 4 we can say is this bar just before, and we'll say that this 2 is represented by 2 bars. We're going to say that all those are equal. We're going to pretend, okay? So this bar that represents this 4 has been divided into 10 equal parts, okay? Those aren't equal, but we are going to assume that they are. Well, if it's divided into 10 equal parts, 4 of them. Imagine dividing a candy bar into 10 equal parts and then having 4 of them. Okay, well, that's exactly what that means. Okay, the 4 in the tenths place literally means the fraction 4/10. There's no difference. Okay, so this we know. So now, what do we know? We know that there is 2 at least, and since we've looked at the 4 and now we know that it's in the tenths place, so that means that 4 means literally 4/10 of a whole number, so 4/10 of a 1, basically. We know that at least our number is 2 plus 4/10. Okay, but we have some more numbers to look at. Why don't we look at the 6, the next number? So the same thing, okay? So if we broke our little candy bar up here into 10 parts, we'll say, well, just like in the illustration before, this one's going to be broken up into a theoretical 100 parts, because I can't actually draw 100 parts, but let's just imagine that this is a candy bar that you have managed to break into 100 equal parts, and you have 6. So a candy bar, 1/100th of a candy bar, or a candy bar broken into 100 pieces, and you have 6 of those pieces, that's not very much, right? That's not very much at all. As a matter of fact, even though this number is 6, it's actually 6 of these little bitty pieces. So it will always be smaller, a lot smaller than the number here. Well, not a lot smaller. If this number was 1 and the next one was 9, let's not worry about that for now. But it will always be smaller, okay? As a matter of fact, we've already established that no matter how many numbers we write out through here, if we even add them all up, they will not even equal 1 of the number immediately to the right of all the numbers we summed. Okay? It's a very key point. So, this 6 literally means 6 1/100ths. We've broken 1 into 100 equal parts, and we have 6 of them. So that's a very small amount. So now what we know is we know that at least our number is 2 plus the 4/10 plus the 6/100ths. We've analyzed those. We know the 4 was in the 10ths place and the 6 was in the 100ths place. And we know that 6 of 100 little pieces is not very much. Okay? 4 of 10 pieces that's quite a bit. That's almost half of the bar. Okay? We divided a bar into 10 equal pieces and we had 4 of them. There'd be 6 left over. 6 and 4, they're not that far apart. So it's almost, we'll say it's less than half, but pretty close to half. Well, 6, if you took 6 away, 6 parts of the 100, you'd have 94 parts. 6 is a lot less than 94, so this is not very much. Okay, so we're adding, the key point here is each time we move places, we go from the 10ths place to the 100ths, go from the 10ths place to the 100ths place. The numbers within those, first of all, they can only be from 0 to 9, right? Because you can't have a 2-digit number in one place. That's impossible. So they can only be from 0 to 9. So regardless of what number it is, unless it's 0, of course, you're getting a lot smaller as you go. Okay? So each fraction that you go, the decimal places represent a fraction. Each number, each decimal place represents a fraction. Okay? And those fractions are getting smaller and smaller and smaller. So I think we probably are starting to see a pattern here. So the 7. Now this is 7 out of 1,000. So we took our candy bar, theoretical candy bar, and we broke it into 1,000 pieces, 1,000 pieces, little bitty pieces. And we have 7 of those little pieces. It's just going to be dust, essentially. Just little pieces of candy bar dust. So even though this is a 7, since it's in the thousandths place, it's actually 7 thousandths. Okay, which is a lot. Even though this 7 is bigger than this 6, we know that it's actually 7 parts of something that has been broken into 1,000 different parts. So this is very little. This is just like 7 little pieces of chocolate dust. Okay? So each number as we go, they're getting smaller and smaller and smaller and smaller. Okay? And that's the point. That is what decimals do. Okay? So now what we know is our number, our 2.467 number actually means 2 plus 4/10 plus 6/100 plus 7/1000. So we are literally just tacking these on to our whole number 2. Okay? So this all means this. Okay? So this slide, this is just to say, we've kind of already been over this, but so the 4/10 smaller than the whole number for sure. Okay? Even if the whole number was 1, it would be smaller. There's no way this first decimal place, okay, so we're 2.467. There's no way this number can ever be smaller, or excuse me, larger than this number, okay? As a matter of fact, the sum of all these, all the way out through here, we can write as many as we want, can never even add up to one of those. It can come really close, but it can never even add up to one whole number, okay? So that is the point. That's the main point. A decimal is just a whole number or a 0. It's any integer with smaller and smaller and smaller fractions added to it. So that's how we tell where our number is, how big our number is. That's how we need to think about it. That's how we tell about where it would be between 2 and 3 on a number line. Okay, it'd be somewhere in there. But it allows us to represent any number that exists between two whole numbers. And there are a lot of numbers that can be between two whole numbers. In fact, there are an infinite amount of numbers that can be between two whole numbers. Okay? We can keep on adding decimal places as long as we want. We can add them for the rest of our lives. We can add so many decimal places that it would take us, our grandchildren can still be adding decimal places, and we will never ever add enough decimal places that will drive that number past 3. As a matter of fact, the more you add, the slower you start moving towards 3, and eventually you're barely moving at all. The more you add, it really doesn't do anything. Doesn't add much at all. So that is, in a nutshell, what decimals are, why, the structure of them, how they're used. Feel free to rewind, fast forward, pause, back up, ask me if you need to. Just ask your teacher. If you didn't understand this lesson, just ask, and I'll be happy to explain it. But I've just seen, I've observed some misunderstandings as far as decimals go. And so I'm hoping that this will clear some of that up possibly and start us thinking down a path that will lead us to true, intellectually satisfying understanding. So what do we always need to do? Is we need to prove something. Okay? So we're saying, or I have presented to you, that 2 plus 4/10 plus 6/100 plus 7/1000 is actually 2.467. So we need to prove that. So to do that, we probably want to convert those fractions to decimals. And we do that by, if you've forgotten, by dividing the numerator by the denominator or the top by the bottom. So we come up with the following. Now you can use a calculator. I would challenge you to pause this and convert each of these fractions to a decimal. Use calculator if you need to. You can do it by hand. Either way, fine with me. So, now, 4 divided by 10, okay? When you convert it, converts to 0.4, 0.4, okay? 2 plus. Okay. 6 divided by 100, hopefully that's what you got when you typed it in the calculator or did the math yourself. And then 7 divided by 1,000, 0.007. So, what happens if we add them all up? Now, let's make sure we remember what we're doing. We're proving that I've shown you that these successively smaller fractions, when you add them all up to the whole number, you get our number with the decimal. So that's what we're proving. So let's finish proving it. So first I'm going to write 2. Just to illustrate, I'm going to add some zeros. We can add zeros, right? 2.000 equals 2. They add no information. I really don't even know why I did that. I just kind of wanted to. Okay, but, well, I do know why I did it, but I like to keep things square, keep things looking. So we're going to add, this is an addition problem. So we're just going to add all these up and see what we come up with. So we'll add the next one. And then finally, we will add the last one, the 7 thousandths. Okay, so we add the first column, we wind up with 7. The second column, all the zeros plus 6 just equals 6. All the zeros plus 4 just equals 4. And all these other zeros plus 2 equals 2. We keep our decimal in the same spot. So that looks like we have proven that it does equal 2.467. So the main point of this is, when you see a decimal and you see decimal places, oh, sorry, that would not make any sense. What we now know, give myself a little room here. What we now know is that even though this has all these numbers, all these big numbers, we know that these first numbers matter so much more than the next numbers, right? Because our fractions are getting so much smaller, and we know these represent fractions. This represents 8/10. This represents 6/10. Okay? This only represents 9/100ths. This one 9/1000ths. So we broke our candy bar up into 1,000 pieces here. We just have 9 little pieces of dust. We broke it up into 100 pieces. We've got 9 little pieces of chocolate. They don't matter. They're never going to really influence this number very much at all. They can, at most, they can almost raise it up 1, but they never actually will be able to. Okay? So the most important thing when comparing fractions is we look at the numbers immediately after the decimal point. If they happen to be the same, then we move to the next number. In this case, they're not the same. One is 8 and one is 6. So we know that no matter how many we add, it never will matter because the numbers are getting so small that they just become inconsequential almost. But not completely inconsequential. So, well, let's just take a minute to process this. So that is why 2.8, even though there are no numbers after it, and it looks smaller than the 2.6999999, that looks very big, but now we know that these numbers are actually start to get very small because they're fractions. They look big, but they're not. Okay? So I said that they become inconsequential, but in reality, they're obviously not inconsequential, or else we wouldn't have decimals at all. So my question to you is, try to think of a circumstance where we would need a number like 2, 4, 6, 7, 5, 2, 9. What are these numbers used for? Okay, if we know, let's see, this is the tenths place, the hundredths place, the thousandths place, the 10,000ths place, the 100,000ths place. This is the millionths place. So if you broke your candy bar into a million pieces, 9 little pieces of candy bar molecules almost at this point, it would be microscopic, I would imagine. So it's not adding much. So why do we even bother with these numbers? So that is your question. So pause it if you need to. Think about it. Think about why we need numbers like this and what they can be used for. So pause it and think about it. Write your answer down. If you were absent, so I need just good notes on this, and then write your answer down to this question. But we'll pretend you just paused it. And so the reason we need these numbers is because sometimes we need to be very, very precise. Sometimes we care about these 9 little candy bar molecules right here. Sometimes it really matters, okay? A lot of things need to be measured very precisely. You can imagine if maybe you worked in a hospital, okay, and you had to give somebody some medication, okay. Let's say you want to be a nurse. That's your life stream, to be a nurse. So you have to administer medication, and the doctor tells you, okay, give Mr. So-and-so or Miss So-and-so 0.006 milligrams of something, okay. And let's say you didn't pay attention on decimal day. You didn't pay attention to my lesson. You thought that you did not need to know that. So you say, well, you know, I knew that it was 0.0 something, so I'm just going to go ahead and give them that. That'll be good enough. Well, you have just given them way too much of whatever they were supposed to have, right? Because this is the thousandths place. So this is 6 1,000ths. So we broke a hole into 1,000 pieces. Whatever this medication is, we took 1 milligram of it and we broke it into 1,000 pieces, and they only needed 6 of those pieces. Okay? Well, in this scenario, what you did was you only broke it into 100 pieces, and you gave them 6 of those. Those are a lot bigger. You just gave them way too much medicine, and you probably killed them. So that's why these are important, because sometimes things need to be very precise, and that's with a whole host of things. Anything you build, any type of machinery, anything like that, a lot of times if something is being manufactured, it has to be manufactured to a certain tolerance, or else the pieces will not fit together. And nothing is ever perfect, and we can't manufacture things to the 1/1,000,000th of a centimeter accuracy, but there is a certain tolerance that manufacturers use in order for things to be able to fit together appropriately. I don't know what those are. You know, it just depends on what's being manufactured and how precise it has to be. But they'll give some kind of specification. You know, this needs to be, 5.278 centimeters across, whatever you're manufacturing, and it could be plus or minus, we'll say, 2/1000ths of a centimeter. Okay, so that would be very precise. You would be right around, you would be between 5.280 and 5.276. Okay, so those would be, as long as you're between that, then your parts would fit together. So decimals really do mean something. They really are important. And so hopefully this helped in understanding them a little bit better, and hopefully I will not see things such as students thinking that this is bigger than that, because that is incorrect. And hopefully now you know why. If you don't know why, rewind, watch it again, pause it, think about it, and if all else fails, well, not if all else fails, actually, if you just want to, ask your teacher. So, okay, so that's it for decimals for now. Hope this cleared some things up. See you next time.